Welcome everyone to today's webinar. We see some familiar faces here. Whether you are a long-time DC fan or just getting started to understand and know DC, we are excited to have you here today. I see the list of attendees growing. Maybe we'll wait a few more moments as participants continue to join. We are right on time to begin. Okay, perfect. So let's go, let's begin. Welcome to Unlocking Direct Current, Mastering Electrical Protection in LVDC Microgrids with CurrentOS. We are thrilled to have you join us today, and our hosts are Marco Carminati. He's Senior Principal Architect for New Energy Landscape Application Lead from Schneider Electric. And we have Ronald Niehoff, who is Standardization and System Architecture Manager from Eaton. So Schneider and Eaton are both valued partners and board members of CurrentOS. We are also here with Prashant Kurup, who is General Secretary of CurrentOS. And I am Raphael Raymond, in charge of marketing activities. So let's begin. Actually, before we dive in the content, I have a few housekeeping notes for you. Feel free to ask any question in the chat. We have set aside plenty of time at the end of the presentation to address your questions, and we will have a discussion, and we will be happy to hear you. For your information, this webinar is being recorded, so your cameras and your mics have been turned off. If you want to interact or if you want to have a more lively session, please feel free to turn them back on. This webinar being recorded, you will receive the recording via email, and you can also access it on our YouTube channel. And this is where you can actually follow CurrentOS news on LinkedIn, on YouTube. We have a vibrant DC community. Stay connected with us. First, maybe let me introduce CurrentOS for those of you who are new to our community. We are a non-profit defining standards for direct current microgrids to ensure reliable and sustainable power distribution in buildings and installations. CurrentOS standardization efforts are conducted in coordination with the IEC, as reflected in our Liaison A status in the SIC LVDC. Currently, we have over 80 partners across 25 countries in North America, Europe, and Asia. We welcome all stakeholders committed to tackling the energy transition challenge. So reach out if you are interested in joining. What we do together. Yes. What we do together is that we are working on projects. The idea is that our ecosystem. I think you are not muted. You think you need to be muted to hear me. We are working on an ecosystem of projects such as office buildings, EV charging stations, parking facilities, university campuses, data centers. It's also street lighting, any kind of situation where we can see the benefit of a DC microgrid. And these pioneer installations are here to showcase what can be achieved with DC, with LVDC. So that was for my short introduction. Without further ado, over to our hosts, Ronald and Marco. The floor is yours. And I think, Ronald, you are the one starting today.
Yeah, hello, welcome to everybody in this webinar on DC electrical protection. My name is Ronald Niehoff, as Raphael already told, and I'm from Eaton. I'm based in the Netherlands, and I'm happy to tell about the CurrentOS protection principles for DC prosumer electrical installations. And let me start with explaining the difference between passive and active DC grids. Passive DC grids are characterized by no power management. They are the traditional installations since decades. There are mainly voltage sources like batteries directly connected to DC circuits. Mostly traditional protection devices like fuses and circuit breakers are used, The architecture of the installations is mostly centralized radial. There is a high fault energy and a high arc risk in such installations, and they are often used in the past, but also still for control systems, supply of critical applications like in IT systems, etc. The picture on the right shows a screenshot from a movie about arc flash. When opening a mechanical breaker, there is a huge arc, and this even does not stop. In AC, as we know, this arc can stop every 20 milliseconds in the zero crossing of the sign, but in DC this does not stop, which makes DC less suitable for mechanical breakers. But since technology moves on, it's also now possible to have such applications done with electronic converters. And what is an active DC grid? The term active in electrical has several meanings, mainly to indicate that circuits are live, but we are using the term active as an indication that there is power management by through control or communication. There are sources connected in such circuits only via converters, so not direct connections. The protection is based on semiconductor circuit breakers, and all kinds of installations are possible. There is a low fault energy, low arc risk, and such installations, such prosumer electrical installations, are used in all types of environments. The block diagram on the right side is a figure from the future IEC 60364-8-82, which is the work of IEC Joint Working Group 44. This is about prosumer electrical installation. There was already an AC prosumer electrical installation published in 2022. And this picture is just to illustrate one of the possibilities for DC prosumer electrical installations covered by this IEC document. The small picture in the middle shows what a short circuit does in an active DC application where semiconductor circuit breakers protect the wiring, and you can see that there is a very small arc occurring even when the cable is able to carry 700 volts, 70 kilowatts. So what is the future of DC grids? How do we see that as current OS? It's the biggest difference is mainly in the last mile. This is already a picture which is used for many years, but it's still actual. The upper part, this shows the situation now where only actually high voltage DC transmission lines occur. So we have not so many DC distribution and transmission in other situations, but in the future, and that's the lower part, there is DC moving from the high voltage into some lower voltages, but mainly, then that's the big difference, we are expecting to have low voltage in the AC applications as well, moving as well in the direction for medium voltage distribution as well. So that is what we expect. So a large, a good future for DC, mainly in the low voltage distribution and also medium voltage. So how will it work? How will future DC grids work? There are a lot of active DC components on low voltage and medium voltage level, and protection and switching mainly is done by semiconductor circuit breakers, as said before, and there is balancing on local level that is done in the active microgrid, as you can see in the blue circle. There are small microgrids which work independently from other energy provisions and independently from the medium voltage and high voltage. But of course, there is some exchange of power sometimes needed to help the active microgrids from getting energy in the situation where there is a low amount of energy available. There is, with this setup, there is the possibility to connect local renewables and storage, and there is also the support of the low voltage and high voltage interaction between the several microgrid structures. I want to explain a little bit on the advantages on such microgrids. So there are a lot of advantages actually for DC microgrids. I cannot explain them all here, but a few I can highlight. One of the most important probably would be the less use of copper. And there is a picture on the right which shows a good infographic from the New Scientist. It's already an article from 2007, but it's still valid, and it's showing how many years we have left of our key natural resources. And for example, copper is expected to be available between 38 and 61 years from 2007 on. But yeah, you can imagine that we are running out of raw materials. So it's an important factor where DC can help a lot. There are some other advantages, like it is difficult to sabotage the missed grids. There is less sensitivity for internet attacks because you are doing power management on local level, and it's suitable to connect all the increased energy demand. So, for example, electrical vehicles. It's flexible and it's scalable, and many more advantages we see. Then about the general DC grid design. The right picture is again from the future 60364-8-82 Amendment 1. But the content of the standard will be very generic. It gives safety recommendations, but not explanations. So it is a good standard, but it is not complete. As you can see on the picture, the scope of the standard will be an prosumer electrical installation with an isolated interlink converter, which is part number 18, with a DC SRC system reference conductor on the DC side of the installation, and the prosumer electrical installation contains loads and sources at the same cable, and that's in fact what we do not do in AC. We have centralized distribution architectures, and we do not combine sources and loads so much on one cable as it is shown here. And as the IEC is quite limited in the explanation, we have in current OS an installation rules document in progress prepared by a special installation rules group, and there we do much more on the explanation of how such prosumer electrical installations how they are working, but the document will also give detailed explanations and requirements for many typical topics like wire selection and fault loop impedances. So how to calculate in practice a real installation. We have also, separate from that, from the installation rules, we have also some technical papers in progress. One is a technical paper on fault protection in multiple distributed sources, DC prosumer electrical installation. There is a concept of this document available. In the technical committee, we are trying to get all the comments done, but the purpose is actually to show how all the types of protection can be covered in a DC prosumer electrical installation. So we are trying to cover all the short circuits between live and midpoint, we try to cover the short circuit from live to earth, so ground fault, and then both high ohmic and low ohmic. So if you have a high ohmic fault to earth, could be also a protection or a direct touch situation, and we'd like to protect all types of faults for DC prosumer electrical installation. And what we have seen already in the document is that with this architecture, isolated interlink converter, central TNS point with the system reference conductor next to the active front end, we can cover all the aspects related to safety for DC prosumer electrical installations. The next slide is about the DC zones concept. The picture is from a MOOC. We have a MOOC with on the CurrentOS website or CurrentOS YouTube channel, and the link I think will be given in the chat. So there are 6 videos from the CurrentOS Foundation on safety, and this one is part of the 4th MOOC. Safety zones are extremely important for us. And why? Because it gives you all the benefit of DC, and that's what we not do in AC. We do not separate high impedance sources from low impedance sources, high energy areas from low energy areas, and that makes it extremely complex to make such installations in AC. And therefore we have this zone system to have the maximum benefit of DC in active prosumer electrical installations. A little bit on the zoning system, however, in the MOOC it is much better explained than I can explain it. Zone 0 is a very dangerous area where no protection is available, and it's going down to zone 3, zone 4, where you have an protective device which is only electronic, so semiconductor circuit breakers only, where you have the maximum advantage of such installations. But again, please have a look at our MOOC, and there is it explained much better than I can do in a few minutes. Also in the MOOC, there is this table explained, and there is a more detailed explanation on what is the difference between the zones. And as you can see, it's also a lot related to the type of circuit breakers. So on the left side, in DC zone 0, there is no circuit breaker at all. So there is the raw source. And to DC zone 1, you come already in the area where a first protection device is situated. And this could be an electrical, mechanical, a circuit breaker, or a fuse. If you go to zone 2.1, there you have similar type of protective devices, only the energy is lower. And if you go to zone 2.2, you see that the disconnection time is again lower. There is the area where hybrid circuit breakers are situated with a disconnection time in a fault situation of less than 1 millisecond. Disconnection time is already that low that this is pretty safe. But if you go to DC zone 3 and 4, the disconnection time, the breaking time is less than 10 microseconds. And that is the area where semiconductor solid state, so not hybrid, solid state circuit breakers only are given with the disconnection time less than 10 microseconds. And you can connect many of such sources with circuit protection, overcurrent protection devices with less than 10 microseconds in such zones connected to the same cable. I don't want to go too much in detail of this table. It's again, it's explained a lot in the MOOC. And so I would like to proceed to the next and already for me the last slide. It's about the breaker, the types of breaker. As I just explained, if we focus for the type of breaker in the different zones, we come to the strong relation between safety risks and break time and speed of opening of such a breaker. So zone 3 and 4 have high speed, 10 microseconds, semiconductor breaker protection where standards are currently developed in IEC. There is an IEC 60947-10 in progress for generic applications, and there is also an 63464-1 breaker family in progress in IEC SC23E, and this is more for residential and similar application. Within the zone 3, there are all types of grid architectures possible, as already said, with combined multiple sources and loads on one cable, and fault protection and protection against direct and indirect touch is guaranteed with bringing all the benefits of DC together. And therefore I close my part of this webinar to say that I'm absolutely believing that safety on DC prosumer electrical installation is at least on the same level as what we already used to in AC prosumer electrical installations. Thank you.
Thank you, Ronald. Good morning, good afternoon, everybody, and welcome also from my side. So now let's talk about protection, rationale, and interlink converter behavior during faults. So here you can see the protection rationales, and in particular on the right you can see the conceptual single line diagram of both AC and DC low voltage distribution. In particular, if we start with the AC distribution, you can see that there are several inductances in series. Some of them are, let's say, the inductances of the cables or busbar system, and the others are inductances of the local AC sources, like, for example, diesel genset, and the equivalent inductance of the AC utility. So, in particular, if we consider the AC utility, in particular the medium voltage AC, having an infinite short circuit power, basically it is the series inductance, equivalent inductance of medium voltage, low voltage transformer. For sure, there should be also resistances in series, but they are not shown as we would like to focus on the effect of both inductances and capacitances. So these inductances, for sure, the source inductances are higher than the cable inductances, have the effect to limit, in particular, the current derivative during a fault, allowing the electromechanical traditional circuit breaker to detect and interrupt the short circuit current. I remind you that usually model case circuit breakers at their breaking capacity have an interruptive time or breaking time of some milliseconds. Instead, larger circuit breaker like air circuit breaker have a breaking time of tens of milliseconds. Instead, if we have a DC distribution, as you can see, there are a lot of capacitances, which are the filter capacitances on DC side. And if we have, for example, a DC bus, like in this case, we can have more than one capacitance in parallel. So in case of a DC fault, we can have a very, very huge current peak according to the ratio between the inductance and the capacitance in our system. But in this case, the current derivative is very, very high. So there is the risk that the traditional circuit breaker are not able neither to detect nor to interrupt the short circuit current. So in this case, solid-state circuit breakers are more effective than the traditional. So when we talk about the DC fault, both short circuit and air fault, usually we can have up to 3 fault stages. The first and second stages are transient component, and instead the third one is a steady state component. The first stage is a very, very fast transient component, and basically it is due to the discharge of the DC capacitor, as we have seen before, installed on the DC side of the AC-DC and the DC-DC converters in our DC distribution system. According to the ratio between the DC capacitances and the inductances, we can have that the system is overdamped, critically damped, or underdamped. In particular, if the system is overdamped or critically damped, basically we have that the discharging current waveform is not oscillating. So basically we don't have the fault stage 2, but we move directly to the fault stage 3. We can reach a very huge current peak due to the DC capacitor discharge, but we don't have the fault stage 2. Instead, if the system is underdamped, according to the ratio, as I said, between DC capacitances and inductances, we can have that the current waveform can oscillate, and as soon as the voltage on DC side reaches a negative value, let's say basically it is clamped by the freewheeling diodes inside the AC-DC converter, and in that case we start the fault stage 2, which is basically a discharge of the energy inside the inductances of our system through the freewheeling diodes of our AC-DC converter. When the inductances are discharged, then according to the, let's say, basically internal architecture of our interlink converter, we can have the third stage, which is a steady state stage. Basically, it is a contribution to the DC fault coming from the AC side, in particular from the AC utility. As you can see, the four stages of 3 ILC categories, as we'll see now. Here you can see the first category of ILC, which includes the non-isolated converter. Basically, in this category, the converters cannot limit the fault stage 3, in both cases of DC short circuit and air fault. In particular, if we have a medium voltage, low voltage transformer neutral earthed, and the DC side unearthed, in particular the positive and the negative, there is a DC earth fault current path through, let's say, the ground connection of the transformer.
Hold on, Marco. For some reason, you're being muted now. Very strange. We could hear you up to now. Yes, we hear you back. All good. Yes. Okay.
So if the medium voltage transformer neutral is unearthed and the DC side, usually the negative, is earthed, the DC air fault can be considered as a sort of short circuit according to the fault resistance. I remind you that if we have a non-isolated converter, we cannot connect at the same time both the neutral of the medium voltage, low voltage AC transformer and neither the positive nor the negative on DC side. Otherwise, we would have a permanent fault inside the converter. Another story if we connect the midpoint directly to the neutral point of the transformer. So in this case, the fault current can have all the fault stages according to the ratio between the inductances and the DC capacitor. The second category includes the so-called isolated converter, but having an architecture made by a combination of an isolated converter, as we have seen in the first category, plus an additional 50 or 60 Hertz low voltage isolating transformer that you can see in this picture. It is not the medium voltage low voltage transformer, usually it is another one. In this category, the converter can limit the fault stage free in case of a DC fault with a medium voltage low voltage transformer neutral earthed and the DC side unearthed. But they cannot limit the fault stage free in case of a DC short circuit or an air fault with a DC polarity, usually the negative, earthed. In case of a DC short circuit or an air fault with a DC polarity earthed, all the fault stages, so the transient, 1, 2, and the third, can be present still according to the ratio between inductances and capacitances. In case of a DC earth fault with a medium voltage, low voltage transformer neutral earthed and the DC side, so both positive and negative, unearthed, we don't have the fault stage free. As you know, a direct current cannot flow through the additional low voltage isolating transformer windings. And also the fault stages 1 and 2 are very low because of the small, let's say, series capacitances between primary and secondary windings of the isolating transformer. I remind you that these are transient components. So theoretically, let's say they can pass through these very small series capacitances. Last but not least, the third category, which includes isolated converter, whose architecture is made by a multi-stage, are able to limit the fault stage free, so the steady state component coming from the AC side, in both cases of DC short circuit and air fault. In particular, in case of DC short circuit on air fault with a DC polarity earthed, the fault stage 1 and 2 can be present. Instead, the fault stage 3 is not present thanks to the limitation, let's say, capability of the inverter installed here on the left side of the high frequency transformer, which is able to limit the overcurrent as a DC fault in our system is seen by this inverter as basically an overcurrent on its AC side. In case of a DC earth fault with a medium voltage low voltage transformer neutral earthed and DC side unearthed, the converter behavior is the same of the converter that we have seen for the second category. You know that for both AC and DC application, if we have a traditional electromechanical system, shall be able to break any, let's say, value of fault, in particular short circuit current, up to the value corresponding to its rated short circuit breaking capacity, called often ICU, with a specific power factor if you are in AC and a specific time constant if you are in DC. Instead, if we would like to select a solid-state circuit breaker, in this case, the circuit breaker shall be able to break any current upon the rate of rise of the current not exceeding the maximum admissible value declared in the product documentation. Basically, it is a maximum VI su dt of our fault current. So no matter about, let's say, the peak value of the current, the maximum value, the steady state value, but here is a matter of the derivative of the current. and also the circuit inductance not exceeding the maximum switchable inductance declared in the product catalog, basically. So it defines a minimum, the I sub T, in order to be able to handle the energy, in particular in those solid-state circuit breaker having a metal oxide varistor inside. So as you can see on the right, if we talk about the solid-state circuit breaker, the critical di sub dt, which can be handled, define the short circuit interruption performance more than traditional rated ultimate short circuit breaking capacity, ICU, that we have with a traditional electromechanical circuit breaker. So some words regarding the protection against electric shock. In particular, let's focus on current OS zone AC installation. First of all, because the breaking time is much faster as we have solid state devices, so less than 10 microseconds. And the related fault energy is much lower, which can bring to a lower arc flash risk, as the incident energy is usually lower than 1.2 calories per square centimeter. So usually no personal protective equipments are required. If we have a TNS distribution like we see later on, an RCD is possible for long cables as fault protection and as additional protection for the direct contact. Anyway, in current OS, we are defining a certification scheme in order to certify the equipment for interoperability and safety and more. So now let's talk about earthing system in DC. Let's talk about in particular system with isolated interlink converter. You know, in DC, corrosion could occur because of the stray currents. I remind you that stray currents are unwanted currents through an unintended path, like for example, the reinforced concrete in building and through the ground, in particular, where they go through the metallic pipes. Corrosion could occur when this stray current leaves the metallic part. So in order to dramatically reduce the risk of having corrosion in DC, we avoid the usage of TTC. And basically, there is a consensus within the DC community on this recommendation. Why? Because with TT system, all the stray leakage current are not directly redirected to the source through a continuous PE conducting path, as you can see in the picture, through the ground. So this phenomenon introduces a voltage drop, which can be higher than 200 millivolt, which is the limit, according to the standard EN 5162, of not having a corrosion risk. If it is higher, like in TT system, there could be the risk of having corrosion. So also TNC and TNCS system are not recommended for the same reason. In particular, here in a TNC system, the load exposed conductive part are, let's say, connected directly to the PEM conductor. That means that also in normal condition, the load current flows through the PM, creating for sure a voltage drop, which is usually higher than 200 millivolts. So also in this case, even let's say with an higher probability than TT, we can have a risk of corrosion. So in current OS, in order to reduce dramatically the risk of corrosion, we recommend the usage of TNS earthing system. TNS earthing system can be unipolar or bipolar. Unipolar, as you can see in the figure on the left, the first figure, are easy to implement with no asymmetry between basically positive and negative or midpoint earthed. But unipolar system provide only one, let's say, voltage and a single point of failure. Instead, bipolar system with a midpoint usually, let's say, distributed, are more flexible as, let's say, they can offer two levels of voltages without having any additional DC-DC converter in our system to supply medium, large, and small appliances or loads. But on the other side, let's say we need let's say a more complex system in terms of control and protection scheme. First of all, because, for example, we have to introduce a 4-leg converter, which is able, let's say, to balance the current inside the midpoint in case of unbalanced load, in order not to have an imbalance in voltages between plus and midpoint and negative and midpoint. And also, if we have a free wire distribution, so a bipolar system, usually we need at least a 2-pole circuit breaker installed on both plus and minus to detect the earth fault current. In current OS, if we have a unipolar and bipolar distribution with midpoint, we strictly recommend to have the midpoint earthed. In terms of galvanic isolation, as I was saying before during the earthing system explanation, the galvanic isolation is, let's say, prescribed by the in current OS in order not to have any mutual fault and disturbances between the DC grid and the AC grid. And moreover, we can decide to connect or not for sure our DC side, no matter regarding the C earthing system. So this is the last slide from my side. So here you can see the typical TNS distribution system with an ILC isolated. So basically we have an AC medium voltage low voltage transformer, which can supply not only for sure our interlink converter, but also maybe other existing AC loads. Then we have the isolating transformer plus the AC-DC converter, and then we have our DC distribution. Here it is electrical installation, so we have locally, not only loads, but also DC sources, like for example, photovoltaic system and battery source, and some other, let's say, active loads, like for example, DC, AC or DC chargers for electric vehicles, with having the function of vehicle to grid or vehicle to building function. Last words regarding IT system. Is it possible in current OS for special installation where the service continuity is mandatory in case of first fault, but it is useful for installation where there are skilled people, and in particular this type of, let's say, installation will be elaborated in the next editions of our current OS system reference document. That's all from my side, and over again to you, Prashant and Rafael, for the Q&A session.
Hello, any questions, please do not hesitate to unmute yourself, and if it is okay for you, you can also put on your camera so we can see you. I already have a couple of questions in the chat. First question, I think both of them are from Guru Prasad. Is there a possibility for simplification of DC fault analysis by ignoring load side capacitances and focus on bypassing source capacitance contribution to limit the overall effect of capacitance contribution on the system?
I don't know if I got the question, but let's say basically here when we talk about the DC fault on, so for sure on DC side, basically you have to consider, let's say, the capacitances of the AC DC or DC-DC converter installed on DC side, which are usually not negligible. And in particular, when we have more than one of them, so more than one converters installed on the same DC bus or DC feeder. Why? Because we have more than one installed basically in parallel, so they can basically sum up their contribution during a short circuit in terms of both current peak and current derivative.
Yes, Guru Prasad, if you want, you can unmute and speak.
Thank you. If possible, like if we focused on the converter itself and the converter design, and we can try to, in a way, through design of the converter, we can preclude the contribution of the capacitor, or in a sense bypass the contribution of the capacitor, so that we can have the traditional circuit breakers, the thermal magnetic or the air circuit breakers interrupt the characteristic that is, consequent of not having the capacitors contributing to the system. I'm trying to think at the converter level too, not at a system level, to solve the problem of capacitor. Yeah.
I mean, if you are able, let's say, per design, to bypass this, let's say, capacitor contribution coming from the converter, and if there are no any additional capacitor installed in our DC system, theoretically, you should not, you could not consider this capacitor contribution, but you have to be sure that this capacitance contribution is not, let's say, affecting the DC fault, or let's say inside your converter there is something which is able to bypass this fault contribution.
Thank you so much, Mark.
Welcome.
And there is also a second question. In TNS midpoint earth grounding configuration, are there any concerns regarding common mode leakage currents?
Yeah, probably I can answer this one. Yes, of course, there are concerns in common mode leakage currents. That is also happening in AC, by the way. But in case where there is a concern, then we can add RCD or RCM, so residual current monitoring, and we can simply measure the fault current. There's the common mode leakage current. We can measure that. On the other hand, we have also, with multiple grounded sources and load circuits, PCR circuitries to separate the common mode from differential mode currents. So in fact, yes, we have measures to prevent from that, and if there is a serious concern, we can also measure it and make improvements so that there is no problem anymore. I hope this answers the question.
Well, system continuity is important, right? I mean, if you are able to measure the common mode leakage currents, but we still want to continue operating the system, we don't want any fault in the metallic grounded parts of the chassis of enclosures. So does the measurement mean that we are going to protect the system by tripping? And if we are tripping, then that means there is no more continuity or the of operation of the system.
Yeah, but usually the leakage currents are very low and are not happening often. If you have a special installation where continuity of service is really important, you probably might switch to IT. So that is also one of the supported earthing systems from CurrentOS. But when it's not a special concern, so in general, prosumer electrical installations are not different from what we have now. And okay, there is a concern, but with residual current monitoring, you can detect it. And if there is something wrong, you can take measures, but they do not need to be taken immediately. If there is 10 milliampere or 100 milliampere fault, there is no need to do it directly the same day.
But we won't have such a concern for a unipolar grounded system. We only have such a concern in midpoint grounded, but this concern wouldn't be there in a unipolar grounded system? Is that accurate, or?
I think it's in every type of midpoint TNS circuits, you have the possibility for common mode leakage currents. It's always possible that when you have a decentralized leakage to earth, there is a possibility that it happens. But yeah, you can detect it. That is actually, and whether it's bipolar or unipolar doesn't actually really matter.
Thank you.
You're welcome.
Okay, so there is also a question about, can you elaborate on factors determining minimum DIDT specification?
Yeah, I can take this one. The minimum DI/DT is linked to basically the maximum switching inductance during the selection of our, let's say, solid-state circuit breaker. Because, the inductance, let's say, has the effect to limit the current derivative. So, let's say, both the current increase during the interruptive phase of the semiconductor itself, but also, let's say, during the current, let's say, discharge inside, in particular, the metal oxide varistor device installed in parallel of the semiconductor component. This, let's say, maximum inductance is linked to also the energy that, let's say, can be handled and dissipated by the circuit breaker, solid-state circuit breaker itself. So here, let's say, from one side, we have to limit the current derivative in order to allow the semiconductor component to open the current, so no matter about the current peak, the current steady state value. But on the other side, this, let's say, can have a counter effect of, let's say, having more energy to be dissipated during the fault inside our solid-state circuit breaker.
Okay. Hope it is clear for Sham, who had asked the question. One more question from Nicola. We are seeing more and more app going on 1500 DC applications and even 2000 volt DC in PV. Is there any SSCB known for such voltage?
I can take this one, then you can complement, Ronald. I mean, so far, solid-state, let's say, circuit breaker for this, let's say, application, let's say, are not, let's say, not present, in particular because I talk about 2000 volt. So far, it is not a low voltage application, but it is still a medium voltage application, even if maybe it is a so-called gray zone. It is no more low voltage, but also from a medium voltage application, it is very, very low. You are right. I mean, in particular, for utility scale battery system and for huge, let's say, photovoltaic system, there is the trend of having this value of voltage, so even higher than 1500 volt. So far, let's say the application of solid-state circuit breaker are at lower voltages. Welcome.
Okay.
Any other question?
Any other question from anyone? Maybe you can elaborate on the point highlighted by Isabel also.
Yeah, basically, yes, I already answered Isabel.
Yeah.
She's right, because there is a typo inside the last single line diagram, because there is a series of external isolating 50Hz transformer plus the symbol of isolating converter. So if we put the symbol of isolated converter, this, let's say, implies that inside our, let's say, converter represented by this symbol, there is either a 50 or 60 Hertz transformer plus a non-isolated converter, or an isolated converter including an high frequency transformer, as basically for categories 2 or 3.
Okay.
Both of them are able, let's say, to disconnect, I mean, in terms of mutual influence, the AC and DC part, in particular with regards to the earthing system.
Okay, thank you. Any last minute question? Thank you, Marco and Ronald. Rafael.
Thank you, everyone. Yes, we are perfectly on time. And if you have questions, we are, of course, always available by email, on LinkedIn. You can reach out to us. If you want to inquire more about CurrentOS, of course, we are here to accept new partners and explain you how we operate. So hope to see you soon in the world of DC. And we have new webinars coming up next month. Stay tuned. Thank you.
Thank you so much.
Thank you. Yeah.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye.
Have a nice
Thank
day.
you. Bye. Bye.